Hey everybody, in this next section we're going to look at some key engine measurements and as well as explore displacement a little bit more than we did in our last lesson. So let's get started. So for starters, when you have done an engine teardown and rebuild, you might remember that one of the dimensions that you checked was the amount of cylinder taper. Cylinders don't wear evenly from top to bottom, as you can see here. They wear a little bit less at the bottom of the cylinder than they do at the top. And do you remember why that is? If you look inside a worn cylinder, there's always this ridge at the top of the cylinder, and there is no ridge at the bottom of the cylinder. It's just smooth. Well, the reasoning is pretty simple. Any oil that the cylinder gets for lubrication gets splashed up from the bottom, and so the bottom of the cylinder gets plenty of oil. The top of the cylinder, though, doesn't get much, and so we get a lot more wear at the top of that cylinder. So one of the measurements that's taken during an engine rebuild is the difference between the diameter of the bore at the top of the cylinder compared to the diameter at the bottom. And the difference between those is called your cylinder taper. And that's some of the easiest math we'll have in this class. The difference between those two measurements is 0.034 or about 34 thousandths of an inch taper. That's pretty excessive wear, but depending on the engine, you could look up what the acceptable amount of engine wear is. And of course, the fix for this is to rebore the cylinder with nice straight walls and use an oversized piston. And we're going to talk more about that a little bit later. The other key measurement to check when you're doing an engine rebuild is the out-of-round measurement. A cylinder will always wear more in this blue direction than the red direction because the action of the connecting rod is always pushing this piston back and forth from side to side, whereas there's really not much force pushing the piston front to back. And so that means that cylinders will always wear in kind of an oblong direction. Now I've exaggerated that, but it'll always wear a little bit more side to side than it will front to back. And too much is of course bad. So to find the out-of-round measurement, we just subtract. Now based on our picture here, the larger of these two, 89.07, that would have to be our larger diameter. And 88.96, that would have to be the smaller measurement. And so the difference between those two is 0.11 millimeters. That would be our out-of-round measurement for this engine. And again, we could compare that to an allowable spec and decide whether or not we needed to rebore that engine or whether it was acceptable. Now let's talk about valve train geometry a little bit. One of the key aspects of engine performance is allowing as much air and fuel as possible into the cylinders to create the best possible combustion. And one aspect of that is making sure that the valve opens as far as possible. So my question for you is, I'm just going to give you a minute to think about this with the animation here. What are the factors that affect how far each of these valves opens up? And that is to say, what things affect what that distance will be? Well, certainly the camshaft is one of those factors. The lobe on that camshaft, the size of the lobe, will push on the rocker arm, and the taller that lobe is, the farther the valve will open. But there's another factor too, and that is your rocker arm. Your rocker arm acts like kind of a lever, and these two distances determine how that lever increases the lift before it gets to the valve. So the main two factors here are your camshaft and your rocker arm. Let's see mathematically how they interact. Okay, here's a formula that you should write down for the rest of this lesson. This is a key one. We can calculate the rocker arm ratio for a given rocker arm by taking two dimensions. The center of the rocker arm is called the fulcrum. Some people also call that the pivot point. When this rocker arm goes back and forth, That's where it pivots. In our previous animation, this is our fulcrum right here. Now we need to know two dimensions to calculate the rocker ratio. We want to know how far it is from the fulcrum out to the valve, and the valve is typically on the longer side of the rocker arm. And we want to know how far it is from the fulcrum to the push rod or the camshaft, which is typically on the shorter side. And so we like to take that longer dimension, y, and divide it by that shorter dimension, x, and that is what gives us a rocker ratio, y over x. So you can write that formula down, maybe make a little picture if you like on your gold sheet or on your temporary conversion sheet. Let's put that into action. So let's figure out what the rocker ratio is for the rocker arm that's shown here. So we already saw that our rocker ratio is the fulcrum to valve distance divided by the fulcrum to the camshaft side distance. Now in our picture, the fulcrum out to the valve, there's our fulcrum, here's our valve over here, that's going to be 2.00 inches. And again, that's typically the longer side of the rocker arm. We're going to divide that to fulcrum to cam. We have a push rod over here, but the push rod is of course pushed by the cam, and that's going to be 1.25 inches. Now if you divide those two, the units cancel since they match. We've seen ratios like that before, and you will get a ratio of 1.6. But 1.6 alone isn't a ratio. Like a gear ratio, we're going to put a to 1 on that, and our rocker ratio is 1.6 to 1. But that's not what this question asks. This question says determine the lift at the valve. That is to say, figure out how far this valve is actually going to open in the cylinder. Well, that requires another relationship. So here's another formula that you can write down. The total lift at the valve is found by taking the lift at the cam and multiplying it by your rocker ratio. Now we already know what the rocker ratio is. We already showed that that's 1.6 to 1. So in order to figure out how far the valve opens, we need to figure out what the camshaft lift is. So let's take a look down here. The lift at the cam is really just the height of this lobe right here. I'm going to redraw that in a different way. Now the 1.385, that's what's called the base circle. That is to say, that's the diameter of the circle where there is no lobe included. And that is this distance right here. But the other dimension that's given, 1.665, that's the distance all the way up to the top of the lobe. And that measurement is of course always going to be more. So the lift at the cam is the distance between those two measurements. That's the number that we really want, the lift at the cam. So to find that, we'll just subtract the height with the lobe, 1.665 inches, minus the height without the lobe, 1.385 inches, and that turns out to be 0.280 inches. That is the height of the lobe on that camshaft. That is what we call the lift at the cam. And now we're ready to go ahead and answer our question. So our lift at the valve is going to be 0.28 inches. That's how far the camshaft moves the rocker arm. And then the rocker arm increases that by a factor of 1.6. You can kind of see that because the rocker arm on this left side is going to move up and down further than it does on this side. In fact, it's going to move 1.6 times as far. And so if you take 0.280 times 1.6, you get 0.448 inches. And that is our lift at the valve. That answers our question. Now, if you want to rewind the video just a little bit, you can watch that explanation again. But the key is that you should have this formula on your sheet. Lift at valve, make sure that one's on your sheet. And then to understand this relationship, this really isn't a formula so much as you just recognizing geometrically that your lift at the cam is just the height of that lobe. Okay, I'm going to give you a minute to do this one on your own. Grab your calculator, your phone's calculator, and a piece of scratch paper. Work this one out, pause the video, and then unpause when you're ready to see the solution. Okay, we want to calculate the lift at the valve here. So, as we just saw, our lift at the valve, we need to know how tall our lobe height is right here, and we need to know our rocker ratio. So let's start with our camshaft. 56.4 millimeters, including the lobe, 39.2 without, we can subtract. And the difference between those two is 17.2 millimeters. So our lift at the cam is 17.2 millimeters. So our lift at the valve starts with that, 17.2 millimeters. And now we're going to multiply that by our rocker ratio. So let's take a look at our rocker arm here. Our rocker ratio is the fulcrum, which is the pivot point in the middle, out to the valve. That's 36 millimeters. Divided by the fulcrum back to the camshaft side, that is 24 millimeters. Again, the longer divided by the shorter, and this time that turns out to be 1.5 to 1 rocker ratio. So we're going to take 17.2 millimeters lift at the cam times 1.5, and we end up with 25.8 millimeters, and that is our lift at the valve, and we've answered the question. Okay, we've already done a little bit of work with displacement, but I want to revisit displacement and do just a little bit more work in this topic. Let's take a look here. We've got a Honda engine that has a bore of 8.1 centimeters, and it has a stroke of 8.73 centimeters. A little bit of terminology we're going to need for our next topic. First of all, when we find the volume of just one cylinder, that one cylinder volume is called the swept volume, and that's an important term to be familiar with for our next topic. So we can calculate this displacement. One cylinder, the volume is found by taking pi times radius squared, that's the circle on the bottom, times the height of the cylinder. We know that our bore is 8.1, and so our volume for this cylinder is going to be pi times, now our radius is going to be our bore divided by 2, so if we take 8.1 and divide it by 2, we get a radius of 4.05 centimeters. We'll slip that in here. And then we'll multiply by our height of 8.73. When you do that, you should get a swept volume, that is to say a one-cylinder volume of 449.86 centimeter cubed. Now we're asked to identify what exactly this engine is. This is clearly a four-cylinder engine, so let's multiply this by 4. And the displacement of this engine is 1799.4 cubic centimeters, but we can also call those cc's, and I'm going to use those interchangeably from here on out. So 1799.4 cc's. That's true, it's about 1800 cc's, but we can turn that into liters easy enough. 1799.4 cc's over 1. Your conversion sheet says, and we'll use this one a lot, there are 1,000 cc's per liter. And if you divide that out, it's pretty evident that is a Honda 1.8 liter engine, very common engine. I just want to remind you here, this is a good place to refresh, but cc's, cubic centimeters, are 2 of 3 equivalent units of measure. A centimeter cubed is the same as a cc. They're different names for the same thing, and that's the same as 1 milliliter, which you often see liquids measured in. So we're going to use that fact pretty often in the next lesson or two here as well. Let's keep going. Okay, let's do another example here. As we already established, sometimes an engine has to be overboard when it's rebuilt. So let's figure out what this big diesel V10 is when it's bored 0.06 centimeters over size. This is a V10 engine with a bore of 10.8 and a stroke of 12.7. So if we picture our cylinder here, the stroke of 12.7 is the height of our cylinder. But here's the key. The original bore was 10.8 centimeters, but it is bored 0.06 centimeters over size. We need to add these two together. So our new bore is 10.86 centimeters. Now you can divide that by 2, and our radius turns out to be 5.43 centimeters. And now we're ready to calculate our result. So as we know, the volume is found by taking pi times the radius squared times the height of the cylinder. That's pi times 5.43 centimeters, which we're going to square, and then we'll multiply that by 12.7 centimeters. Take a minute and do that. Verify that you get the same thing I do here. About 1176.4, and those are cubic centimeters or cc's. Now that's a 10-cylinder engine. That number right there, 1174.6, that is our swept volume, but we want to find the displacement. So let's multiply that by 10 cylinders, and that becomes 11,764 cc's. That is our displacement. But the question here asked us to find that displacement in cubic inches and in liters. So let's first find that displacement in cubic inches. We're going to take 11,764 cc's. Now, a conversion fact that we're going to use an awful lot here is the fact that there are 16.39 cc's per cubic inch. That is a really important one. That one's on your gold sheet, and if not, make sure that that one is on your temporary conversion sheet. That trades in our units of cubic centimeters, and that means this is a 717.8 cubic inch engine. It's a big one. Now let's also find that in liters. Now let's not start from cubic inches. Let's start from, again, the displacement that was in cc's. 11,764 cc's. You can put that over 1. Again, off your sheet, we've used this one before. There are 1,000 cc's for every liter. And so the math on that is pretty easy. That's going to become 11.76, or about an 11.8 liter engine. And there, we've settled that. We're done. Okay, our last two problems tie together here. I want you to take a minute and do this one for practice. I want you to tell me the swept volume and displacement of this engine. It's got a bore of 3.910 and a stroke of 3.310. Go ahead and do that. Unpause the video when you're ready to see the solution. Okay, we know the bore is 3.910, and therefore our radius is 3.910 divided by 2, which is 1.955 inches. So since all cylinders have a volume given by pi r squared times height, hopefully you'll have that one memorized, we use it so often, then we can find the swept volume by saying that that volume is pi times our radius of 1.955. These are in inches, we'll just keep that in mind, times our height, which is 3.310. That turns out to be 39.7, and those are cubic inches. There, we found the swept volume. Now let's figure out what engine this is. We can only see 4 cylinders here, but this is a V8, and so there's 8 cylinders on the other side as well. And so let's multiply this by 8. And if you multiply that out, you get 317.95 cubic inches, which if you're a Mopar fan or a Chrysler, you know that that is a 318 cubic inch engine. And Chrysler used a lot of those engines in cars and trucks and vans through the 70s, 80s, and 90s. Okay, now let's tie that into one last question. I want you to go a step further with that and tell me, what does that 318 become if you do a rebuild and have to bore the cylinders 30 thousandths of an inch oversize? It won't be a 318 anymore. Go ahead and calculate that new displacement. Pause the video, resume when you're ready to see that solution. Okay, our original bore of 3.91 gets the oversized bore added to it, so our new bore is 3.94. If we divide that by 2, we get a radius of 1.97 inches. And now we can go ahead and finish the problem. So our radius of 1.97 gets combined along with the height of 3.310. That does not change, by the way. 3.310, the height doesn't change. And so our volume here, our swept volume, is going to be pi times our radius squared times our height of 3.310. And that gives us 40.36 cubic inches. That's each cylinder. This is still a V8. And that 318 is now 323 cubic inches. No real rounding rule for displacements. Usually go to 1 decimal place maybe, and oftentimes with cubic inches it's rounded off to the whole number as I did here. Okay, that wraps up this topic. You can go ahead and do the appropriate problems as given in Blackboard, and we're going to continue this idea a little bit when we deal with compression ratio in our next unit.